Hello everyone, I'm Pedro. I'm a PhD student at Conditional in Brazil. And right now I'm doing a 6-month internship here with Mauro, funded by Brazilian institutions and so on and so forth. And I have this work on some form of feature information we considered from a simple question that seems to have some interesting insights about the physics of the problem. I'm not so sure if it's useful for anything, but I don't care. I just do it for the fun of doing it. And this is like the subtitle of my presentation is why some random parameter with some sort can be like good physical insights. So my presentation will be in this manner. I won't talk about the outlook of the presentation because it's better to rush. Just because someone asked me, I come from the northeast of Brazil, from a state called Piauí, which is not so famous as Rio and São Paulo, so I wanted to talk a little about it. It's a very nice place. I'm from the city. By the way, my grandma's house is in this photo in some places. But it's a famous city because of being very hot. It's very, very hot. Like the thermometers here, for instance, are showing like 55 degrees Celsius and 44 degrees Celsius. And this is like, it's not always like this high, but it's always above like 30 degrees Celsius, which is like, I don't know how we can study these conditions, but we do. And there are some nice places such as Serra da Capivara, which have many archaeological sites, and Delta Parnaíba, which is the only delta in for open sea, open ocean delta in America.
The sea, I think not sea, just the name of the sea.
Teresina. Anyways, you're invited to visit this state whenever you want. Of course, I advise you to be careful because of the temperatures. And now I live in Rio, in a nice place. PUC-Rio is a fantastic campus. Of course, if you are in Rio, you're invited also to visit us and give some lecture or talk to us. And the Pope is my boss. This is because it's Pontifical University. But these are my collaborators. This is me, in a nice picture my girlfriend took. This is Fernando Yamini, my co-advisor from Federal University of Fluminense Federal University. Diogo, which is a professor at University of São Paulo. Silvio, which is from this Brazilian Center of Research in Physics, and Welles, which is my advisor at PUC. So just to contextualize something to you all, stochastic thermodynamics is an area that has began to exist since the late 90s, I would say, and it stems from the fact that you have at mesoscopic scales like stochastic dynamics. And these mesoscopic scales are in the region between atomic and are not macroscopic, but can be, like, for instance, microscopic. For instance, the Brownian motion was conceived in that region for Poland, and since the 90s, people saw that the behavior of systems at that scales could be described in terms of some energetics that would give some interesting results. For instance, fluctuation theorems, which were discovered first by people, for instance, Cohen, Galafavotti, and these other guys, and later Jarzynski and Proofs. And these fluctuation theorems say that because you are in some mesoscopic scales, and your dynamics is stochastic, the physical observables are stochastic, gain a stochastic character, and as such they obey probability distributions, which are like obey the conventional thermodynamics on the average. So these probability distributions. Of course, with some irreversibility, you have like you can find like forward and backward distributions because the error of time is emerged in that kind of dynamics, and you can observe that, for instance, for the second law of thermodynamics to hold, you need to have some pseudo violations of the second law. Actually, they are not, but in the sense that you have like energetic free lunches. Another stuff, since the discovery of the fluctuation theorems, which were the first big results in stochastic thermodynamics, many things emerged. For instance, thermodynamic uncertainty relations and speed limits on thermodynamic speed limits, which are like central to my own contributions. On another side, since like the 80s, the 70s, some people were working on geometric thermodynamics or differential geometry approach to thermodynamics, mostly for classical and equilibrium ones, where the metric is given by by the fluctuations of internal energy, and you can define some kinds of lengths where the points of the described by these lengths are equilibrium probability states. And you can find some distinctions between lengths, and proofs in 2007 showed that the Fisher formation on the situation of for equilibrium probability distributions holds well as the Fisher formation metric holds as a metric that can define those thermodynamic lengths. Most of his work was made for equilibrium distributions, and he derived also the deviations from the geodesics, which are this J here, and some relation between these deviations from the geodesics and the squared length, which are some sort of uncertain relations and some sort of in the end of the day, they are simple limits. All his work in this paper was just for near equilibrium situations. Later, he's shown with David Sivak that given that you are in a canonical ensemble, etc., you can show that those relations between the deviations from the geodesic and the stochastic length are a relation between the excluded word and represent an infinite bound for the excluded the excess word, which is the word that doesn't convert into free energy. Okay, so this was for near equilibrium and for equilibrium only, but Ito and at the same time, Belmonte's group and so other people derived these kinds of relations and this kind of interpretation for Fisher formation for situations far from equilibrium, where you have, for instance, that the Fisher information for time as a parameter as the contributions of you can represent some as the average of the time variation of the entropy that outflows to the left, and some thermodynamic conjugate force which came from no. This case is thermodynamic force, like F is the thermodynamic force. But and he's shown, for instance, for a three-level model that this holds the description for Fisher information and also the speed limit that is always smaller than the time, so you have a type bound for. Sorry.
Thermodynamic force is connected with some thermodynamic potential.
Yeah, it's as far as I remember, it's the derivative of the thermodynamic potential to some. It's the thermodynamic force, for instance, in Gonzaga theory. And he's shown that this holds for far from equilibrium. More recently, Letitia and John Gold Leticia Beckman and John Gold show a quantum version of that, also showing, in the end of the day, that, for instance, this interpretation for Fisher information is most likely the case where you take only the contribution of the populations, but they show for some independent fact that these relations and this speed limits also hold as well. So just to give some reminder on stochastic thermodynamics, the name stochastic arises from the fact that you have stochastic dynamics. In the sense that your dynamics, for instance, on trajectory level is described by, for instance, Langevin equation. In this case, I take some Langevin equation with Gaussian white noise. Gaussian white noise because I don't want to complicate things too much for yet. And you can, of course, obtain some probability distribution for the position, which will, in this case, always be Gaussian. And if you take some beam here, you always have some probability distribution which is Gaussian for the position. And as I said, the thermodynamic quantities will also be stochastic in the sense that they also follow probability distributions. For instance, this is for heat. This is a case for potential energy, and you can have also for work and other more conventional thermodynamic quantities, work and heat, which people have observed in the past that experimentally observed that the fluctuation theorems. For instance, this was for Jarzynski and this was for Kurz. And we asked a very silly question. Normally, the stochastic thermodynamic prescription is to treat the thermodynamic quantities as stochastic quantities and look to their probability distributions. And we have like Fisher information, which was a coordinate quantity like for metrics and for primary round bounds and tours and so forth. What if we consider some stochastic Fisher information? For me, personally, it sounded very ridiculous, but I went to it anyway. But it was not so ridiculous. Just to give some idea, Fisher information is known for being related to primary round bound because if you want to estimate some unknown parameter in your system that your probability distribution contains some information on it, you can have some lower bound for the variance of some estimator you have given by the inverse of the Fisher information. In our case, for the stochastic Fisher information, can we do something like that? Most probably no, because to derive the round bound, we got a very high average. We don't have the average. So as far as I know, it's not useful for that. But why should someone care for stochastic Fisher information or for conditional Fisher information? Because first things first, considering the stochastic Fisher information, you have a probability distribution for instance, this is a protocol where you consider some saturation force, and for the force and for the time, the characteristic time, we could see that this is followed well. On the average, you have the Fisher information expected, obtained analytically. But the stochastic Fisher information can be thought as some stochastic measure, and this is not something new. In relativity, some people have considered, for instance, in this paper, the fields expanding in some stochastic way, following some Langevin equation, and you have some stochastic corrections to the gravitational constant. For us, as far as I remember, we could do some stochastic lengths and stochastic deviations from the average, something like that. But this deviation doesn't have any sense of a deviation from the geodesic because we cannot establish some geodesics in these systems. As the stochastic equations are not integrable. but we began doing some interpretation of some non-equilibrium thermodynamic interpretation of the stochastic Fischer formation. And by looking at the description of the Fischer formation given previously by Ito and some other people on as some form of difference between the average variation of entropy from the bath and the average the variation of thermodynamic force, we arrived at by doing some algebra and noticing that this derivative is something like one part of the contribution of the time derivative of the stochastic entropy. We arrived at that the fact that the thermodynamic interpretation for our case was pretty similar to the Fischer formation case. Moreover, sorry,
What's S?
sorry.
What is S? S squared.
It's just a way to put magic. Actually, this is not a fraction, by the way. It's just a magic. Just a magic.
It's the dynamic.
It's linear. Yeah. Yeah. I just put this dt here just to simplify the equation. But it's not a derivative, by the way. But looking into the for instance, using some Gibbs distribution, you have that the stochastic Fischer formation by the end of the day represents the contributions for the variance. And these contributions for the variance, for instance, on equilibrium limit are physically meaningful in the sense that you do not have a metric, but you have the contribution to the metric, something like that. This also holds, by the way, to the continuous case. We derived before for the discrete case, but also holds for the continuous case. And then we can establish, knowing what this is, some sort of speed limits on trajectory level. Like for each of the realizations of your experiment, you have some speed limit, which is delimited not by the average Fischer information, but for this one Fischer information. Like, and you can establish also a hierarchy of speed limits from the averages of this speed limit on trajectory level. And testing this for instance, some Brownian overdated Brownian particle following some protocols which that comes from equilibrium and go for equilibrium, we can see that the speed limits on trajectory level when there's some saturation for the thermodynamic speed limit, they don't have some probability to violate the average speed limit, but when you do not saturate the speed limit, you can have some stochastic speed limits that saturate that go beyond the average one, the thermodynamic one. We saw this for both cases we worked on. And then we arrive at this kind of relationship chart, which is you have some Fischer formation, which is an ensemble average, which defines some length. You have also some stochastic Fischer formation or conditional Fischer formation, which is on trajectory level, and you can define trajectory level length. And for both of them, you have some speed limits, but you cannot recover one of the other, but they follow relations between each other. In our case, as expected by the stochastic Fischer formation interpretation for a given state, for instance, is that the speed limits are some sort of contributions to the autocorrelation functions of the derivatives. And it's worth mentioning that the stochastic lengths also follow some fluctuation theorems, which are actually this is wrong, but which are information on geometric fluctuation theorems, different from the cases that are worked before, because they have some geometric character. And we are also like doing a quantum generalization, and in the end of the day, when you when you rewrite this probability distributions, some trace of the POVM over the symmetrics, you see that this is just a information. And so I was pretty fast. I'm sorry, but we can discuss. But we have many next steps. One of them is that we do not have some figure of merit for those speed limits on trajectory level, as well as some non-Markov. We do not know yet what are the non-Markovian effects on these things. And this kind of information geometry is stochastic in the sense that the metric is stochastic, but I really don't know differential geometry, so I really don't know how to like formalize this kind of stuff. So it's still unexplored, and yeah, I try to sell that this may be nice for machine learning because you have things on trajectory level and it can be less costly, but I'm not sure too. And the experiments, we are doing some collaborations with people on optomechanics in Brazil to try to see if this experiment can help, like the speed limits and also the fluctuation relations. So yeah, just sitting hardy. I don't do useful stuff. As far as I know, and I don't know if this is important at all. But thank you. This is it. Yeah. I'm sorry for being last in the rush, but I know we have a meeting after that, and I don't want to take much of your time. So yeah, that's it. So, yeah, questions.
What about the your treatment is valid independently of the linearity or non-linearity system? If you wrote a dynamical equation like Langevin equation.
Yeah.
There is inside there is a linear term or non-linear term.
In principle,
Just in quantum mechanics,
it's linear, but it's in principle it's general. Like this framework is very general. Like, but I mean the output I don't know.
No, because normally to manage from both quantum mechanical or classical, for example, in this case, naturally, if you have a linear term, you can make analytical treatment.
Yeah.
But if there are some nonlinearity,
Sure.
even if the deterministic differential equation can be not solved, So this is what if there is, because you should make some theoretical approximation technique.
Yeah.
Just to try to have some in.
I mean, I agree, but in principle, should be general. Yeah. The only difference is, of course, the fluctuation theorems will hold in principle, because the only thing you guarantee is that the initial quantities are perfectly or something like that.
So sometimes the nonlinearity the system can have influence on the amplification of some fluctuations.
Yeah. Like some resonance or something.
Oh, yes, some amplification in general.
Yeah, sure, but yeah. In principle, this is very general. My answer for now is just I don't know what the difference would be.
So in some sense, you cannot predict.
Yeah, exactly.
And probably this conflict is.
I'm sorry.
That's fine. So just to understand, so you are assuming that you have a stochasticity in the sense that you have a probability distribution which depends on time.
Yeah, yeah.
And the fishing information is stochastic in the sense that you have this probability distribution.
Yeah.
That's and then you derive from this fishing information a sort of metric, so it essentially is the metric,
Yeah.
which just to understand.
No, that's precisely it.
So what you are saying is, I don't know what's the meaning of this fishing information, or what physically it's, what is the, what?
I could say that this information is related to the contributions, like for instance, if you consider it to be some sort of variance, like
I mean, you can attach to this stochastic instantaneously. You have a probabilistic distribution, whatever it means. It is well defined in a sense.
it's like you are tracing out the other, like you are marginalizing the distribution on time. Like you have a.
Why not generalizing the signals? You already have some.
Let me see if I find it. Okay.
You consider time as it's not just a parameter, but it's also.
You can treat time as a parameter.
You have a stochastic process.
Yeah, you have a stochastic process. You can treat time as a parameter because the position will not depend on time, but the average position will have dependent on time after you marginalize it. For instance, if you pick like just a beam of this thing, you have a Gaussian distribution that you have like marginalized over the whole process. So the probability distribution is not directly time dependent, but it has some information about the time. That's what I mean. That you are like. I mean, the correct name is, it should not even be stochastic fish information, but like it's some conditional fish information. Like it's conditional in the sense that you are just taking a part of the information you have on X, for instance. And I don't know if I'm being clear enough.
If I understood, this is not an average over fisher information.
Yeah.
It's like you take the fisher information, which is defined as an average, and you take the simple elements in the average.
Yeah.
It's not like you have a fisher information that varies in time with some distribution.
But
You can put the formula on the slide after this one. Because it's not there.
Oh, yeah.
This one. Like, this is the conditional / stochastic feature, right? The one below.
Where theta is in this case?
it can be any parameter you want to estimate. There's a parameter to be estimated.
Parameter what?
That you want to estimate. The parameter that you want to estimate, like in problem scenario. But it can be
easy, which is okay, we call it somewhere in the physics of the system.
yeah. And then the time is just a way people put to say that this is a metric and you can like evolve in time.
This is classical, right? It's not
This is all classical. Yeah.
So can you understand the f theta is like if you change a little bit the parameter theta, f of theta is how much the probability is change in each metric corresponds.
So far this is all standard feature, right?
The first one, yes. The second one.
The second one is sorry.
This is because
Is
it's
it inside the probability? Okay, is the form? Okay, is there already?
it's the surprise rate. Yeah, this part. Yeah.
Okay, and so you're okay. So you call this sort of stochastic?
Yeah, in time we call stochastic information because the information behind was stochastic. But in the end of the day, this is just a conditional thing. You are just taking one of the positions or one of a part of information, if you can say that, and you are looking because this is the average of this thing, which it's weird, but it's only a part of this is like a number. When you average, you are doing the average over all possible numbers and so on. Yeah. So that's the stochastic information.
So then, again, where is the time over here?
You can say that
It's very inside
X or T.
Yeah, theta can be dependent on time, and to simplify stuff, you can say that this is purely the time. Like that. Let's see. Here, if you have this lambda dependent on time, you can transform this derivative into derivative in lambda times the derivative in time, and you can say that this lambda is time. In the end of the day, I understand that's marginalizing the joint distribution of all possible positions during all times in terms of only one time. You know. That's why there's some parameters to be estimated under quotes, because you don't know which time it is after marginalizing the distribution. So that's it. Which, by the way, made me confused too in the beginning. Sorry? By the way, made me confused too in the beginning, but now it's clear for me.
No, just a point of clarification. So you're saying that this stochastic or conditional Fisher information represents a good metric in this interpretation. So it can be interpreted as a metric out of the competition.
Yes, no, because it's random, right?
But then at some point it seems that you write some yes, but
Yeah.
sort of line element depending on this quantity.
Like here, for instance. Yeah. Yeah, it's a metric alternative to the Fisher information metric, but in some sense we do not have control of it. In the same way you have control of like Fisher information as an average quantity, right? Here we do not have an average. So, for instance, if you look at the lengths that are given by those quantities, and now I can say like fully the length given by this is stochastic, because you are following some stochastic dynamics, and then the length over some random quantities is a stochastic quantity. In that sense, it's a metric, but
could you say maybe in the language of differential geometry, could you say that somehow that since you are considering a stochastic process, it's like your manifold is changing in time,
yeah.
And so you need to have
exactly.
So this is correct.
Yeah, yes, correct.
Maybe just a connected question. What is the definition of a stochastic metric? So is it like a metric on average, or it's
It's like a metric on number. Yeah, as far as I know, yeah. Any more questions? I'm sorry, everyone. I don't know likely information geometry is applied for instance, for control field, but in this case, it's quite difficult to apply for that case. But I think like as this is related to the score, and you have those stuff like the fluctuation theorems and so on and so forth, can be some alternative like to use on machine learning. And there's some nice stuff coming out with here. The fluctuation theorems, for instance, are purely geometrical. They aren't like work or heat or something like that. No, it's far from equilibrium. But to guarantee some detailed fluctuation theorems, you to make evolution work. Yeah. That's my point about saying equilibrium, but it's arbitrarily out of equilibrium. Yeah, that's it.
Any other questions?
No.